1.10 Piecewise Functions and Step Functions. Today, students will construct piecewise functions, they will graph piecewise functions, they will analyze and relate characteristics of piecewise functions to applicable situations. Piecewise function. The definition is a function made by combining other functions, much like connecting pieces of railroad track end to end. Each section of a piecewise function has a corresponding interval of x values associated with, which is also similar to domain. So if we look at this piecewise function, you can see that there are 1, 2, 3 different equations, all within the same brace. We are going to put all 3 of those on our graph. So you can see equation number 1 is this first line. Equation number 2 would be this piece in the center. And equation number 3 would be this piece on the far right hand side because it is only looking at the values greater than 1. When we graph a piecewise function, we want to graph each of the pieces individually. So remember, when we graph linear functions, we're using y equals mx plus b, m is our slope, b is our y-intercept. So looking at this first function, we have x plus 1. So I know my y-intercept is 1, my slope is up 1, right 1. But then we only want a piece of our line, and that piece we want is all the values that are less than 1. So x equals 1 right here. We have an open circle because it's a less than symbol, and all the x values less than 1 are to the left. You then erase the other side of the line. Looking at piece 2, we have a y-intercept, again of positive 1. And this time we are going down 1, right 1. Always run to the right. We want all the values between 1 and 3. So x equals 1 right here. We want a closed circle because it's or equal to. X equals 3 right here. We want an open circle because it's just less than. And all the values between there would be right here. Everything else on our graph we want to go ahead and erase. So we only want that one specific piece. Looking at our third equation, it also still has a y-intercept of negative 1, excuse me, and it is rising 1, running 1. We want all the x values greater than or equal to 3, so x equals 3 right here. We want a closed circle on our graph at that point because it's or equal to, and all the values larger are to the right. You want to erase all of the values, other lines or marks you use to graph this equation, or this piecewise function. We then need to state where our graph is decreasing. So if we look at the red line, our graph is decreasing, looking at our x values from 1, including 1, to 3, but it's an open circle, so we use a parenthesis. Our graph is increasing on the blue line from negative infinity, and it is also increasing where our yellow line is, going to positive infinity. So we can say from negative infinity to, but not including where x equals 1, or our yellow function, I'm going to write it in blue so you can see it, from positive 3, including 3, to positive infinity. Going backwards, in example 2, we want to write the equation of the piecewise function as identified. We then want to state the domain. We want to state the range, and we want to also list where it is decreasing. So we want to look at it piece by piece. It doesn't matter which piece you start with first, but make sure yourself a note so you don't accidentally write the same piece twice. I'm going to start with my middle piece first because I can easily see where it crosses my y-axis, so I know my y-intercept is a positive 3. I then can use my slope triangles, and I know that my slope rises 1 and runs 1 every time, so I have 1 over 1x plus 3. I then look at my x intervals from negative 3, x is between or equal to negative 3. It is not equal to positive 3 because it's an open circle. Looking at my next piece, I'm going to look at this piece right here. Again, using your slope triangles, you can see where these intersect. So I can see that it would intersect my y-axis at 0. So I have plus 0 for this top line. My slope is, it is rising 2, running 3, so 2/3 x. And it is coming from negative infinity, so I want all the values. X is less than, not equal to because it's an open circle, negative 3. Looking at my third and final line or piece, I can see that my slope triangle goes down 1 over 3. So my y-intercept would be positive 2. My slope is negative 1 over 3x. It includes 3, so x is greater than or equal to 3. After we have our function written, we then want to look at our domain. So when we look at where our function is coming from to where it's going to, we can see that it covers all of the x values from negative infinity to positive infinity. When we look at our range, we're looking at our y values. What is the lowest y value our graph touches? What is the highest y value our graph touches? Up top, it has an open circle that it goes through, so it is only going to be, it goes to 6, but it doesn't include 6. And then we touch an arrow down here at the bottom, so we say it's negative infinity to positive 6, but not including 6. Looking at which lines on my graph are decreasing, I can tell that line 1 is increasing from negative infinity, line 2 is increasing, line 3 is our only line that is decreasing. So from positive 1 to negative infinity, including positive 1, so this needs to be a brace, it is decreasing because you're looking at your y values. Example number 3 says this piecewise function represents the speed at which a squirrel ran along a fence. Chris only watched it for 8 seconds. Graph the function. On which interval is the speed increasing? So the first piece of our function that we're going to look at is this top piece. So we know that our slope is up 1 over 1, and we're starting from 0, 0. And the squirrel ran at the, up 1 over 2, excuse me, and the squirrel ran at this rate for 4 seconds. So when we get to 4, our line stops. It's a solid dot on 0, an open dot on 4 because it's an open, or it's not equal to. Our second piece is t minus 2, so our slope again is up 1 over 1, but we start at negative 2. So if we go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. From 4 seconds to 6 seconds, including 4 seconds, but not including 6 seconds, the squirrel ran at this rate. Looking at our last piece, we have just including 6 to 8. He ran at a constant speed of 4 feet per second. On which interval is the speed increasing? Well, we can see both the purple and the red lines are going up. So we can say that it is increasing from 0, including 0, to 6, but not including 6 because it is an open circle on that. 4 is a constant feet per second speed, and the only inequality that would satisfy that is not an increasing inequality. Example number 4 says, as of January 2017, the price to mail a first-class letter was 47 cents for the first ounce or less, and 21 cents for up to each additional ounce. Roughly sketch the graph of this piecewise function and write its equation. Why do you think we refer to this as a step function? So it said for 1 ounce or less, it cost 47 cents. So at 1 ounce or anything less than that, we would pay 47 cents. So on our graph, we would draw a horizontal line. We want an open circle where it touches the y-axis because we are not going to pay any money if we don't ever ship a letter. We want a closed circle on 1 because anything up to or including the first ounce is 47 cents. For every additional ounce, we add 21 cents. So if we then add 21 cents to 47, that gets us 68 cents. So again, we have an open circle on the left side, a closed circle on the right side, because for 1 ounce, we don't want to pay 68 cents. We still want to pay 47, but anything over 1 ounce, we will pay the additional 21 cents. As we continue adding 21 cents, we would have an open circle on the left, a closed circle on the right, and you can see that this appears to look like stairs, which is why we call this a step function. So when we write our equation, we want all the values greater than 1, not equal to 1 because we are 0, because we have an open circle on 0. Then when we think about this equation or this step function, we want to add, we are always going to pay a fee of 47 cents, and then we are going to pay the additional 21 cents for every ounce that we add. But we don't want to pay that additional 21 cents for our first ounce because it's included. So we want to write x minus 1 inside our parentheses is equal to our function. So when you plug these values back in, we are only want to pay our 47 cents for our first ounce, and every ounce after that we only want to pay an additional 21 cents, which is why you need to be careful not to flip-flop your locations of your 21 and your 47.